Okay, picture this. We want the cheapest, simplest and most efficient way to see a place from above, like a farm or a construction site. So how do we build something that can hover in the air, stabilize itself, capture photos or videos and send the footage back to the ground? The answer is clear: UAVs. Fixed wing, rotary wing or hybrids. Among all of them, the most affordable to fly is the ancient lighter than air technology, airships or hot air balloons. You can easily build one with just a helium balloon from a party store, a lightweight camera, a few servos and a propeller. If you don't have batteries or simply don't want to use them, you can tether it with a wire that supplies power and data from the ground. The goal is to maintain a stable observation position above a target, using only a single downward-facing camera. No GPS, no LiDAR, just one eye looking down. Let's dive into the principles. Every autonomous system starts with perception. First things first, we need to figure out how the ground beneath the airship is moving. We use orb, oriented fast and rotated brief for feature detection. Orb is lightweight and efficient, which is critical for real-time processing. It finds unique corners and texture in the frame, but detecting features isn't enough. We need to track them from one frame to the next. To match features across frames, we use a FLANN matcher. FLANN stands for Fast Library for Approximate Nearest Neighbors. It helps us to find which feature in the current frame correspond to features in the previous frame. We filter these matches using Lowe's ratio tests. This ensures we only use high-quality matches to estimate movement, which brings us to the heart of the estimation, visual odometry. Once we have our good matches, we calculate a homography matrix. This is essentially the mathematical presentation of how the ground plane has shifted between frames. By tracking this shift over time, we can tell how far the airship has drifted. Raw visual odometry is noisy. Imagine a gust of wind shaking airship or dust on the lenses. The system would freak out and think it just teleported. We don't want that. To handle this issue, we add Kalman filter. The Kalman filter is an algorithm that takes a series of noisy measurements over time and produces estimates that tend to be more accurate than any single measurement alone. In our code, we set up the Kalman filter to predict the airship's next position x and y based on its velocity. We tell the Kalman filter to predict the position. If feature matching fails, which it will on blade featureless surfaces, we use the prediction. If feature matching succeeds, we feed that measurements back into the filter to correct the state. This fusion of prediction and measurement makes the path much smoother and more robust. We also include a moving average window to smooth the path even further. By averaging the last 30 positions, we reduce jitter, making the control system's job easier. Now we have a position estimate. How do we turn that into commands for the airship? We need to determine whether we've drifted from our target point. In our control loop, we calculate the difference between our current smooth position and the target position we want to hold. If the drift exceeds a certain threshold, we generate a movement command. For example, if the position shows we drifted right and down, we command the airship to move left and up. This error signal becomes the input to a PID controller. You can see the path plotted in real time on the right. This lets us visualize the drift and the corrections, a beautiful presentation of the system's mental map. While this is already a huge step for me, the future holds even more challenges. What happens when the ground has no features? What if it's water or just sand? That's where deep learning and optical flow can step in to replace or complement traditional feature detectors. The beauty of this open source approach is that you can take this code and adapt it to your own blimp, drone or robot. Experiment with thresholds, try different feature detectors and see how robust you can make it. And finally, thanks for watching.